Good morning to all, and welcome to Atal sponsored FDP on development and application of sensors in modern life in day 4 session 1. So the name of the speaker in session 1 is Dr. Kana M. Suresan, Professor, Aizer, Thiruvananthapuram. The title of his talk is Sugar Derived Gel for Various Applications. Dr. Kana M. Suresan is a professor of chemistry, Aizer, Thiruvananthapuram, Kerala. He obtained his BSc degree from Payanur College, Payanur, and MSc from Sri Narayan College, Kannur. Further, he received PhD degree from NCL Pune. He has joined in IISER Thiruvananthapuram in 2009 and now serving as a full professor in the School of Chemistry, IISER Thiruvananthapuram. Professor Kana has received various prestigious awards in national and international levels. Some of them I listed here, such as JSPS Postdoctoral Fellow at Ithim University, Japan from 2002 to 2004, Research Officer at University of Bath, UK from 2004 to 2006, AVH Postdoctoral Fellow at Max Planck Institute for Molecular Psychology, Germany from 2006 to 2008, then Swarna Jayanti Fellowship, DSD Government of India 2013, Ramanujan Fellowship, DSD Government of India 2010, Fellow of Royal Society of Chemistry in 2012, Young Scientist Award MIT USA 2015, Alexa Humboldt Fellowship he also received in 2008, and now recently he received the Technology Innovation Award Ministry of Chemical and Fertilizer Government of India, and many more. Sir, I could not listed all, so some of them I listed here, sir. So his research interests include the supramolecular chemistry, topochemical reaction, methodology development, and natural product synthesis, chemical biology, etc. He had guided 7 PhD students, 2 postdoctoral students, 11 numbers of MSc students, and presently he has guided 8 PhD students, 4 MSc students, and 1 postdoctoral students. He had published more than 90 articles in peer-reviewed journal and published also some book chapter also. So now I would like to thank Sir Professor Kana M. Suresan for accepting our invitation. And now, sir, I request you to present your work, sir.
Thank you, Dr. Atal, for the introduction and also for the invitation. I have to share my slide. Do I have permission for that?
Yes, sir. Sir, you have permission already given, sir.
Okay, I will share.
Yeah, it is sharing, sir. Yeah, now.
Is it coming?
No, sir. First, you just open in the PPT slide and then you just share. Now it is fine, sir. Now it is fine.
Great.
Yes.
Thank you. Yeah, I have slightly changed. You can hear me, right?
Yes, yes.
Thank you. Yeah, so I have slightly changed my title to incorporate some of the other research I am doing. I hope you are okay with that. So once again, thank you for the invitation. And we work on, as mentioned, as the introducer mentioned, we work on supramolecular chemistry and also natural product synthesis. Mainly our work is on supramolecular chemistry, but we also do natural product synthesis like small carbo sugars and other natural products which are biologically active. Today I will be talking some part of supramolecular chemistry, mainly on gels, the area of gels. It's not moving. Okay, so gel is something in between liquid and solid. A phase in between liquid and solid, you can say, or a state of, you cannot say it's a state of matter, but it's some phase in between solid and liquid. For example, if you take solid water, it doesn't have a specific shape, but it takes the shape of the container. But once the container is gone, it doesn't have the shape. That means it's flexible, it has enough flexibility. So when you come to, and they are not very strong, when you come to solid, they have very rigid shape, they are not flexible at all, and they are much more stronger. And gel is somewhere in between, actually. So it will take the shape of the container and it will retain the shape like solid. Basically, it is having a solid and liquid phase. So we'll see what exactly a gel is. A gel is uh, actually it has both the solid part and also the liquid part. Usually the solid part is fibrillar network, very minute solids which you cannot see using naked eye unless you use scanning electron microscope or other microscopes. And in the mesh, water or some solvent is congealed or trapped. That is what is a gel is. This is a gel we usually encounter in restaurants, etc. This is edible gels, which is made up of collagen. It's a protein-based gel. About more than 95% is water, just 5% or less than 5% is collagen, a protein-based gelator actually. This is a polymeric gelator. Now coming to the classification, there are polymeric gels and also low molecular weight gel. The one polymeric gel is this one, the gelatin. This is a hydrogel. That means it can gelate water. And also there are other polyethylene glycol is also can form gel, higher polyethylene glycols. Then comes to low molecular weight organogelators or hydrogelators. These are small molecules, very small molecules, usually less than 500 molecular weight. And they can also form self-assembly to form fibrillar network. They are not polymer themselves, they are monomer actually, but they can have a non-covalent polymer actually in some solution. And that non-covalent polymer make a mesh, and in the mesh the solvent get trapped. That's what a low molecular weight organogelator is. So there are two types, of course, the organogelator and hydrogelator, which depending on the solvent with which it forms gels. So these are molecules which you all very well know. This is the first one is glucose, sugar. The other one is its own isomer, but it is a carbocyclic cyclitol. You can say it's an inositol, myoinositol it is. And the last one is mannitol. These are different forms of sugar, you can say. They are very rich in hydroxyl functionality, and because of which it is highly soluble in water. The moment you put them in water, they are soluble, highly soluble. So they are useless for a supramolecular chemist, because once you put in water, they will make an isotropic solution. There is no self-assembly possible with these kinds of compounds in water. And in organic solvent, they are insoluble because of the high hydrophilicity. Now we can do some chemistry here. We can do some chemistry by adding some groups. Here we have added a thiotollyl group in the glucose anomeric position, and also a benzylidine group at the 4 and 6 position. Can you see my cursor also when I move the cursor? Yeah.
Yes, sir. Yes, sir.
Okay, good. So these are hydrophobic components, and this is the blue one is hydrophobic component. Now this we have made it as partially hydrophobic and partially hydrophilic. So we can say it's an amphiphilic molecule. Similarly, in acetol, you can put two acetone molecules and make this diacetonide, or you can say diketal. And similarly, here two molecules of acetones were added to get this diketal. This is mannitol diketal. So also this is another ketone we have added here. Cyclohexanone to make this cyclohexyl ketone. So these are all amphiphilic molecules now, partially hydrophilic, partially hydrophobic. Now they are soluble in some non-polar solvents. Still they have hydrogen bonding possibility because there are OH still left there. So they can form hydrogen bonded network in a non-polar solvent. That network like this is only a schematic. Actually, the dumbbell you see with the two OHs is the schematic of the molecule on the left side. Now the dumbbells having OH will hydrogen bond form a chain, actually hydrogen bonded chain, and such hydrogen bonded chains you can call it as a fibril. Several such fibril laterally aggregate and form much more thicker fibers, and such fibers entangle in 3 dimension and will get a fibrous network like a spaghetti or noodle like network. And there are a lot of spaces in between, and in the spaces the solvent goes and get trapped there. That is what a gel is. So the gel has both solid and a liquid component. So I will tell you some applications and some gelators we have prepared in the lab. Uh, So initially we started with sugars or sugar type molecules. So first one is here. So this is a mannitol derived gelator having two acetone units added, the diketal actually. This is a good gel for various oils and non-polar solvents. This is the gel in pump oil actually at 1 weight percentage. So you can see this is stable to inversion, it doesn't flow out. Now, on the right-hand side, what you see is the concentration-dependent NMR in a gelling solvent. Benzene D6 also, or benzene also, this is the same molecule gels. So with increasing concentration, you can see I have changed the concentration from 3.86 to whatever on top, 49 millimolar. So what you see here, this is the OH signal. These two OH signal appears here at low concentration. But increasing the concentration, you can see there is a shift. There is a downfield shift of the OH hydroxyl signal. This says that this is an intermolecular hydrogen bonded self-assembly. So this is almost at the gel state. You can see there is also line broadening because it's becoming more and more viscous, and finally it's a gel. So then you won't get good NMR. So you can clearly see this the shift that says that it is intermolecular hydrogen bonding, and also this is IR spectrum of the same gelator in different scenario. Actually, this the blue one is chloroform solution. Chloroform, it doesn't form gel, so that means they are individual molecules. The hydroxyl stretching appears around 3,500 centimeter inverse here. But this is the gel actually. This is benzene gel, and this is also zerogel. Zerogel means you make the gel and remove the solvent. The solid, what you are left with is the zerogel. So in those cases, if you take IR, there is a shift actually for the OH structure, and this also says that this is due to the intermolecular hydrogen bond. This is the microscope image of the gel. If you remove the solvent from the gel, what you get is a zerogel or aerogel, you can say. And if you do scanning electron microscopy, you can see this kind of fibrillar fibers in the gel. Okay, so this I have already mentioned. So here, so this gelator, if you make gel out of this, and this is in paraffin oil, this is 5 centimeter thick gel block actually. This is the structure of the gelator. Both are identical structures, chemtro structures. On one of them, I have placed a 5 centimeter thick gel block made out of the same material and paraffin oil. You can see both the structures very easily. That means the transmittance or transparency of this material is high and the transmittance is high. This is the transmittance data in the visible region of the spectrum. You can see from 400 to 800, about 90% of the light is transmitted. And in the UV region from 400 to 200, you can see completely absorbed. So it's basically this is a UV filter. So if you pass through, if you pass light through this material, it will filter out UV by absorbing and give us the good light. The safe light, which is the visible light. Why this is absorbing is because paraffin oil is a byproduct of petroleum industry. So there are a lot of aromatic substances present in that, and those aromatic substances are absorbing this UV. So anyway, so let me proceed. So this is having a high transmittance. That's more important here. So we can make all kinds of shape depending on the container you're using. And now it is almost like glass. It's a glass like gel. So now another important point is anything people are looking for glass substitute, soft glasses, a jelly type of glass substitute. But two important things is one is transparency or transmittance. The other one is refractive index. Water is also very transparent, but you cannot make a glass substitute from water or ice because the refractive index of water is so poor. The refractive index of glass is 1.5 and refractive index of oil is also 1.5, most of the oils. So if you make an oil gel, that can be a possible glass substitute, provided it is transparent. Now we have a gelator which can make a transparent gel in different oils, and this can possibly be a glass substitute. We have checked the refractive index of this material and we found that it is 1.46, which is nothing but 1.5. So we have glass like gel. Can we substitute glass? So that is the question next. Also, this we found that this is having a self-healing property. So what I meant by that is if you cut this gel into several pieces and put them together later, this will self-heal. After some time, you can't see the boundary. So this is an experiment here. This the particular one on left side is a gel block which we have cut into 3, and after some time it's healed. You can't see the boundary actually where it was cut. Now to visualize that, what we have done here is we have taken the middle piece and daubed with pyrene. Pyrene is UV active, as you know, and in the UV light you can see 3 different blocks here. Also, we can make many such pieces together. I mean, this is 18 different blocks, disc actually, small disc we have combined. I mean, put them together after some time, it's self-healed. The 18 discs, the alternate ones are daubed with PTC or peroxyl tetracarboxylic acid anhydride, which is colored substance. So you can suspend them vertically or horizontally, they are stable, they are self-healed. So now this is good for our application. What application? Application is the optical application. So we have made different structures. Here is a gel tower. This is a henge, gel henge, like Stonehenge in UK, you know. And this is a cone, all kinds of structures you can make. And also you can cut them, you can handle them. This is, you can handle them, you can take in your hand. There is no issue with that. Now we have made some optical devices. Here we have taken 3 glass slides and tied them together using the sellotape. Now we have poured a hot solution of oil gel to this, and after some time it'll when it cools, it will make a gel. Then you can remove the sellotape and also the glass slides. What you get is a prism of gel. Now also, if you have a watch glass, you can pour a solution of this oil, and after some time what you get is a planar convex lens. Now, I have already told you that these gels have the self-healing property, and if you put 2 planar convex lens face to face, what you get is a double convex lens. This is a double convex lens which you can read my name, which is magnified compared to the other part. So this is a functional optical device made from this gel, and this is the prism again from gel, and you can see the Whitgier pattern here. So there are possible application, of course, UV protective goggles. This particular gel has this UV filtering ability, so we can make a UV protective goggle out of this. And also there is another application, especially biologists use oil immersion microscopy. The reason for this is at higher magnification. The object is here, what they want to see, whether the bacteria or some specimen is here, the eyepiece is here, and so objective lens is here. The object is here, objective lens is here. And between the objective lens and the object, there is an air column, actually, airspace. Again, the refractive index of air is poor, and refractive index of glass is 1.5. And there is a difference in the refractive index, and the light can change its path, as you know. And that will cause aberration, chromatic aberration, that's what is called. Especially at higher magnification, the data you get is unreliable in terms of the scale and the position, etc. So what people use is to put a drop of oil, so that oil is having a refractive index of 1.5, which is that of glass. So that will cover the space. Now the problem with oil is a liquid, and after some time, if you want to have long time observation, after some time it will spread out depending on the viscosity of the oil, and that is a useless thing, and you can still have air gap. So now what we have developed is an oil gel which you can cut into any piece. You can make a cylinder of our oil gel and put it here, and that's stable for any time. Also, this is possibility of using adaptive optics. Actually, we can change the curvature of the lens by heating and cooling, and by changing the curvature of the container. This is only a prospective application, and by which you can change the focal length of the lens. And this is what we do. I mean, our eyes can change the focal length by changing the curvature of our eye lens. So such adaptive optics can be visioned from this kind of soft optical devices. Another application I want to talk to you about is phase selective gelators. Phase selective gelators are if you have two phases, for example, water and oil phase, oil and water phase. And if the gelator selectively congeal one of the phases, that's called phase selective gelator. So now we are interested in phase selective oil gelator, specifically gelling the oil part from a mixture of water and oil. Why they are important, I will come to that soon. So this is another gelator which we have made in the lab. Again, you can see the gel picture and also the hydrogen bonded intermolecular hydrogen bonded assembly, and also IR spectra, which I have already briefed with another compound. It's the same signature you can see here also. Also the microscope image, you can see the spaghetti-like network, very random three-dimensional network with a lot of space wherein the solvent get trapped. Now this is a phase selective gelator. It can congeal only oil from a mixture of oil and water. Now that such materials have, it was proposed that these materials may have application in oil spill recovery, marine oil spill recovery. Marine oil spill is a big issue actually. Most of the, I mean, whichever the country is having a coastal line are under threat of oil spill, and it happens every time in the history. Many times it happened, and it causes a lot of problem. When it can happen by accident. We had a Chennai Ennore accident 2 years ago, which was a very small scale accident. About a few tons of oil got leaked into the sea. That was just an accident. But there can be much more oil spills because of eruptions in the soil, I mean in the sea, and also most of the oil rigs are in the sea actually. In the Gulf countries, oil rigs are in the sea. If there is an accident, there will be tons, thousands of tons of oil. I mean, thousands of tons of oil will get into the water, and that will spread in no time, and it will cause a lot of problems to the flora and fauna of the marine flora and fauna. And that will also get, because this crude oil have a lot of toxic metals also, like arsenic and mercury, etc. That can come to higher organisms, including humans, by consuming this fish or whatever seafood, and also birds, etc. And all these marine flora and fauna will die if there is an oil spill. And also secondary problem, which I have already mentioned, it can come to terrestrial organisms also. The usual procedure to tackle such oil spill currently is just to burn it a bit. So if you put fire, it will immediately burn. Most of the burnable substances will burn, and it will spew a lot of carbon dioxide, carbon monoxide to the atmosphere. That will again pollute the atmosphere. And non-burnable, non-flammable substances will get down the sea, and again it will come to our system. So that's not an ideal solution. And also, burning oil is not a good thing, because burning oil means burning money. You know the petrol price, right? So it's very expensive. This expensive substance is burning money actually. So that is not an ideal solution. An ideal solution can be if there is a material which can take this oil selectively, absorb this oil selectively, and we can reuse that oil. So phase selective gelators were proposed, at least in the lab scale, that if it forms gel, we can separate the oil from water. So we have also shown that this is, I will show you the video better than this picture. This is a diesel and water mixture actually. I think it's better with the video. Next one is a video. So this is what you see in this container is seawater, and what we are adding now is diesel, measured volume of diesel. Now my student actually, the hands are of my student. So he is dissolving something by heating. You can see some solid substance at the bottom of the RB flask. That is the gelator we are talking about. So he is dissolving the same thing in diesel actually. It's soluble in diesel. So we don't want different phases here. So that's why we are using diesel as the medium. Now he is spreading over the diesel layer. This is diesel water layer already. Now he is spreading this solution over the diesel layer. You can use a hand sprayer also, which also we have shown in another time using a bigger what you can say bucket actually. So now after some time he's checking whether it is jellified or not, it's congealed or not by putting a coin. This is euro coin. Euro is very, very dense. So since it is floating, it's not sinking. So that means the gel has already been formed. Now you can use anything and you don't need to use also. It's sure that it will gel. So what now you see something is coming out. He's taking something out. So that is all the diesel we have put into the system. All the diesel initially you have put also for the spray also we have put some amount of diesel. No, that is coming as a disk. So now you may ask, how can you use this diesel? So it's very simple because you know that this is formed by a weak hydrogen bonded gelator, which you can easily break by heating actually. Mild heating, you will get the oil back. So that's what he's showing now. He's crushing that. This is diesel, jellified diesel. Now he's slowly heating that. Also measuring how much he has recovered it. And it was 97% of total oil we have put. The 3% is not here actually. The 3% went as a vapors while heating this material. So this is working fine. This is just a proof of concept. Now there are issues actually. In oil spill, no one puts oil, petrol or diesel in the water. Very unlikely. And when it spills, it's a crude oil, which is much more thicker, which is much more corrosive, which has a mixture of substances, which is really, really tarry material. We have to show with that. Next, another problem is you have seen that he was dissolving this material in a solvent, which itself was diesel, and you have to spray aerially in a real scenario in oil spill, marine oil spill. You have to use a helicopter to spray this one, and that's very risky actually. Having this petrol or diesel in a hot condition on in a helicopter is not very safe affair. So these are the problems. Now let's see how we can solve this. I don't know why it is going again. Yeah. So the issue was that we needed a carrier solvent, which was diesel itself in this case. Now we have tested about 18 different gelators we have made in the lab. And in one case, we found that this can be directly applied as powder. When you apply directly as powder gelator, what happens is the powder gets jellified just on its surface actually. And most of the inside part of the gelator, the solid powder, is inaccessible for the oil and it doesn't make an effective gel. So it's important that this powder gelator spreads throughout. So we could only find one particular gelator that can be directly used as powder without any carrier solvent. So now we have solved the issue of carrier solvent. And in this case, we have used, I think I have video here also. In this case, we have used real oil, crude oil. So here, water again, seawater. That is a crude oil. That is, we are adding that. Now that is the substance. This is a glucose-derived substance. You can see the structure also. Now he's directly adding as powder, spraying as powder, spreading as powder. So after some time, you can see that you can scoop out this jellified oil. Now, what you see on the side is because while taking out it is touching the sides of the beaker. But when he put the camera just above, you can see that water is very clean. He will put the camera just on top now. Yeah, right. So this is water is clean, but the side is a little bit murky because of this jelly nature, and it is difficult to take out. So now we have improved. We don't need a carrier solvent, and we can directly do it in real crude oil. So next is now there is still problem. Consider this situation in a ocean where the oil is spread over thousands of kilometers, and this kind of jelly material is formed. How do you take out? When you scoop out, they can break into small jelly particles, and it's not easy to handle this kind of semi-solid material. So again, we need to improve. We need a carrier actually. So that's what we have done here. Here we have used here we have used a carrier, which is nothing but recycled paper, cellulose. This is also recycled newspaper. And in one of them, we have embedded our compound actually, the gelator. In the other case, we did not add anything. So now let's see. So the right side is with the gelator, this one, and this is just a control without gelator. We wanted to avoid the problem of handling this oil gelator. The jelly oil. After some time, about half an hour waited actually, we can scoop out all the oil actually. So this water you can in principle drink. There is nothing here, no oil here. And here it doesn't work because we don't have gelator. Gelation is very important actually. What is happening is it is absorbing all the oils surrounded by this one, and then the gelator start acting and it will make a gel, and it will make a rigid gel. Even if you suspend this one for hours or days against gravity, even a single drop of oil will not come out until you press it. Now, how do you get the oil back? Just press it. If you press the oil, this material will get all the oil back, and you can reuse use for fractionation, and you can get petrol, diesel, all those things. So this is much better. Now we are still improving on these areas actually. This was when we published this, United Nations got interested, and also our Indian Navy, Indian Coast Guard, and also some companies interested in this kind of work. We are trying to improve this further. Again, it's going to the same thing. No, I don't want that. Yeah. So another application is carbon dioxide absorption. So can we make material for carbon dioxide absorption? This is another area where environmentally, for environment, it is dangerous, right? Having high levels of carbon dioxide, and people are concerned about that. So how can we clean this carbon dioxide or take the carbon dioxide? Carbon dioxide is a very useful material actually. If you can collect them by reducing carbon dioxide, you can get formic acid, formaldehyde, methanol, etc., even up to methane processes. So you can use value-added materials out of this waste, which is dangerous. Carbon dioxide. So people are looking for substances which can absorb carbon dioxide. The best substances known so far is calcium oxide. We know calcium oxide plus CO2 gives CaCO3, that old physical chemistry equation. So that is a process, is a solid the solid calcium oxide will absorb carbon dioxide and become calcium carbon. It's a crystal to crystal process. So the calcium oxide has voids actually, through which the carbon dioxide goes, and it will become calcium carbonate, much more bigger molecule. And upon heating, you can remove this carbon dioxide, and again it will go back to calcium oxide. So you can redo this process back and forth, and you can get carbon dioxide from atmosphere. The problem is After a few cycles of heating and cooling, this becomes amorphous, not crystalline, and there is not enough pores. So this process become inefficient. Only the surface activation happens. So that means only the calcium oxide in the surface of the material will become calcium carbonate. Most of the calcium oxide inside will be calcium oxide as such. So this process is called sintering, and this is bad. So ideally what we want to make is increase the surface area of calcium oxide. We thought we can use our gel chemistry. How do we do that? So it's here, this is the gelator. TOS, so tetraethoxysilane, is a solvent which can form gel actually. Also tetraethoxysilane, if you hydrolyze, you will get silicon dioxide, silica. So this is a precursor for silica, and also this is a gelling solvent. So we made gel out of this one. And after some time, if you put a little bit of amine or even just weight also fine, after some time, this tetraethoxysilane will start hydrolyzing and it will form nucleate silica around this fibrous particle, which is made up of this one. You know the mechanism of gelation, right? It will form the fibers. So around the fibers, it will form silica. And after some time, you can leach away this one, wash away this one. What you have is a cylinder, a hollow cylinder of silica. So in that hollow cylinder, this is of micrometer size. So that means we can have nanocrystals, grow nanocrystals on the silica surface. By simple, by simply taking calcium chloride and ammonium carbonate solution, we can grow crystals of calcium carbonate on the silica tubes, both inside and outside. And upon heating, this will give nanocrystals of calcium oxide. Now it will have more surface area. It's expected that it will have more efficiency in terms of carbon dioxide absorption. This is the silica TUS gel. This is the SEM of silica tubes. Actually, you can see they are hollow tubes after removing the gelator. And this is the TEM, actually transmission hollow. Tiny crystals actually. And you can also characterize at each level. This is only silica you can see from EDS, and also this is calcium carbonate stage, and this is calcium oxide. So at each stage you can, using powder XRD, you can characterize this material. So this is calcium oxide crystals on nanocrystals on silica microtubes. We have used this material for carbon dioxide absorption, and it has about 33% of calcium oxide on silica. So this is the first absorption, about 23% by weight. Then it slightly reduces in the next cycle, slightly reduces, and it is stable about 12 to 13% over 30 cycles. This is the 30th cycle. You can still continue a number of times. So more than 10, 12 percentage of by weight it can absorb, and you can redo it. If you take same mixture, actually same mixture in the sense 33% calcium oxide and silica dioxide, and physically mix them without nanocrystals, you see that initial absorption itself is bad, about 15 to 16 percentage. Next one it goes to 12 percentage, and third it goes to 10 percentage. Now over 30 cycle it is less than 5%. This is 5% mark. This is less than 5 percentage. So there is an effect of this nanocrystallization, and we have shown this in this particular paper. Another application I want to show of this gelatus is as a metal ion scavenger. Of course, you know this is a crown ether. They bind potassium, sodium, etc. These kind of alkali metal ions, and there is a lot of interest in removing potassium from high potassium rich water, because hyperkalemia can cause a different, hyperkalemia is a state of disease actually, when your potassium levels goes up and a lot of other problems starts. So one has to remove excess potassium if there is excess potassium in drinking water. So this is a very good material which can complex actually, crown ether. But unfortunately, this crown ether is soluble in water. So you cannot use this in water because this itself will be soluble. Now people have solved that issue by adding some hydrophobic benzene unit. So this is dibenzo crown. This is insoluble in water. But here the problem again is you need a biphasic extraction. You need to dissolve this in an organic solvent like chloroform. and then take out the potassium from water layer by shaking in a biphasic extraction manner. Because if you take directly solid, what you see is that yes, absorption is that this is only a potassium picrate. Actually, the yellow color is picrate. So if you dip in this tablet in potassium picrate, only the surface activation happens. So it takes potassium picrate only in the surface. Most of the inside of this crown either is inaccessible for potassium ion. So again, we want to make sure that this material is porous so that the potassium along with the water can reach inside and maximum efficiency can be obtained. So we thought we can use some gel chemistry. So fortunately, all these benzo crown ethers are gelators. We found them as gelators and they form all kinds of fibrous structures as I have shown here. This is the SEM picture. Now our idea is here. So we take styrene. Styrene is a gelling solvent for this particular crown ether gelator. And also this is the other gelator which we have made previously, mannitol gelator. We take both the gelators using styrene as a solvent. Now both will form its own fibers actually, because this use CHO hydrogen bonding for self-assembly. This use for OHO hydrogen bonding. So they self-sort and they form self-assembly here and form gel of this styrene. I have shown in different color actually. Now styrene is a monomer for making polystyrene. Just if you put AIBN or any other radical initiator, a speck of it, a small crystal of it, it will crystallize, it will polymerize. So now you have a polymer, which is polystyrene. And also in the polystyrene matrix, you have this kind of self-assembled gelators. Now, one of the gelator is our crown ether, which is required for the removing the metal ions. The other one is just to make channels actually. How do we make channels? Just to wash it away. Just take the solid cube and wash away with methanol or even water. This is water soluble actually. So it will go. This gelator will go, and in where the places there are this gelator, it will make channels. Now what you have is a porous polystyrene matrix in which you have crown ethers inside. So this is a SEM picture of that. And we have used this material, this tablet actually, out of that porous material. This is the UV absorption data initially picrate solution. After one dipping, it goes to basal level of 0.1 absorption. So you need 2-3 times of, 2-3 seconds of extraction to make it to about 90% completely you can remove. Not completely, 90% potassium you can remove. This is again, so this is before dipping this in a cuvette actually, potassium picrate. This is white in color. After dipping, this takes most of the color, and this is after dipping that. So this is one method we have shown. Another interesting area is fabrics, conducting fabrics. People are interested in conducting fabrics, especially in cold countries, Europe, etc. Maybe also North India. In the cold season, when it is ice, when it is the water is frozen, you have a lot of static electricity generated. That can cause a lot of damage to the machinery and also human beings. That's a huge problem in cold countries, especially dry weather. So now, people are interested in making fabrics, conducting clothes, which can dissipate this static charge. As and when charge is developed, it can dissipate. So people are interested in making conducting clothes. So before that, I will tell you for showing you the other chemistry here. Topochemical reaction is a reaction in the crystal or in a self-assembled state. It's not in an isotropic solution where you need a solvent. There is no solvent required. It is in the crystal and it's due to the proximity. If the reacting groups are at proximity, they will react on its own or with some mild activation using or dialkyl, right? So if they are assembled like this at this distance, about 5 angstrom between the monomer units, and also at this angle, 45-degree to the normal. So they will undergo this kind of one for polymerization. What you get is a E9 actually, fully conjugated E9, which is conducting actually. It's called PDA, polydiacetylene. This is a conducting polymer. Now, if we have this conducting polymer, yes, that's good for static charge dissipation. Now, how do we plan this one? How the challenge is here? How do we align this monomer in this particular in solution? It's impossible. In crystal, it's possible, but in we don't want to do it in crystal. We want to do in gel. Gel is also possible, so that's what we have shown here. This is Shinkai's gel, glucose-based gel. He has also shown that this is having this when you crystallize this one, you can see the methyl, which is shown as this bold, stacks one over the other. We thought, why not we change from methyl to this kind of diene units? Then diene will stack one over the other. That's what we require actually for this reaction. So we have developed this gelator, very similar to Shinkai's, only difference is methyl versus this diene unit. And this is what is expected. That's thereby we can place these two at proximity. Then upon shining light, what you get is a polymer, polydiacetyl. Why we have chosen sugar is because our cloth is also nothing but sugar. Cotton cloth means glucose. So it can nicely hydrogen bond and anchor to the cloth. And it can polymerize and it can have anchoring at multiple position and it will be a strong anchoring. So we have made, yes, this is a good gelator. You can see the gel picture. Upon shining light, you can see this is completely polymerized. This is the PDA has a color actually. This is the PDA color. Of course, you can also measure the, understand the polymerization using IR or Raman actually. So this is again UV studies also you can see these are the signatures. This 537, 584 signature for polydiacetyl formation. And also IR and Raman spectroscopy also you can use for this specific signature of this E9 molecule. So it's a complete polymerization upon this shining this light. Now this is our idea. So our cloth is nothing but cotton. Cotton is nothing but glucose. Cellulose. Cellulose is nothing but glucose. Now this gelator also having a sugar motif can nicely hydrogen bond like this with the glucose. And also it can place this one at proximity. And upon shining light, this should make a polymer which is anchored to the cloth. Now this is what the proposal again in a schematic. We can take this gelator and dip a cloth in this one and shine light and you will get a conducting fabric. This is the real data. Actually, this is the conducting polymer, conducting cloth we have made. You can see the PDA color. And this is one individual fiber, two different, this is ident then this is without doping. You can see the surface resistivity is 10 to the power 8 ohm per square. So that is sufficient. That means it is a semiconductor. That is sufficient enough to dissipate the static charge. You can also reduce further by doping iodine. So that also we have shown in collaboration with a physics colleague here. Now let me see my time. Yeah, we have time. So another application is topochemical acid alkane cycloaddition reactions. So this is another topochemical reaction or Huygens reaction, you can say. Huygens reaction is acid and alkane undergoes cycloaddition reaction, 1,3 dipolar cycloaddition reaction. You get a mixture of products actually at very high temperature in solution. So you have a mixture of 1,4 and 1,5 disubstituted thiazole. There is no selectivity in this reaction when you do at high temperature in solution. Now, we can do this in topochemical way. Why we are interested in this particular reaction is it has a high thermodynamic drive, about 65 kilocalorie per mole actually. It's an exothermic reaction. Nevertheless, it has an activation barrier about 20 kilocalorie per mole. So that means just mixing acid and alkane will not react. You need some heating. So that's why this 20 kilocalorie per mole. And this is possibly the transition state for this cycloaddition reaction. And if we have some scenario like this, it will automatically react without even heating much. So this kind of arrangement is possible, not in solution, but in crystals it's possible. Also in other self-assembled medium like gels. So we want to explore that here for making this kind of polymers actually. And let us see what polymer we can make using this. So yeah, I think this is the first, this is in solid. I will just go through this. Yeah, here. This particular diphenylalanine based peptide having this azide and alkane, it's a good gelator. It's a good gelator for many non-polar solvents. And this is the gel fiber. You can see a CM image. And also you can see it's a hydrogen bonded network, as I have already told you for other sugar-based gelators. Now, this is the crystal structure, and in the crystal structure, these azide and alkane from adjacent molecules are proximal for them to undergo reaction to form a polymer. So this, when you heat this gel, I mean zero gel, you see that this is completely reacted. This is a IR spectrum with time-dependent IR spectrum. You can see the signature for azide slowly vanished because it's used in the reaction. It completely formed polymer. And one interesting thing you see here is there is something coming with the progress of reaction. This is actually progress of reaction. Some water is coming. So that means it is taking water from atmosphere during the reaction. Actually, what happens is this particular, this is the crystal structure. We have seen that during the reaction, it takes from water from atmosphere to fill a void actually and form a hydrogen bond. And that water can be removed very easily because it's a hydrogen bond with a triazole nitrogen. And at very low temperature, you can remove. And again, after removing, you can keep the material outside and within no time, again, it will catch water. Again, you can remove. So this can harvest water. Such material which can harvest water are of lot of interest actually. Now, about 40% of the world population has access to water throughout the year, fresh water. After 10 years, it's only 10% of the whole global population will have access to water. So now people are looking for some solution for this uh, problem. The solution, one of the possible solution is take water from atmosphere. Atmosphere has a lot of water. 6 times water present in our bodies, so that much water is there in atmosphere. So there should be technology to take water from air. So people are working on MOF and other materials which can take water from, for example, Omar Yagi and co-workers are doing that. Metal can catch water and that you can recycle, do several cycles. So basically tapping water from atmosphere. The problem with such MOF material is, of course, these are metal organic frameworks. You don't know the stability of this metal organic framework after a few cycles of hydration, dehydration. And also, this water will be tightly coordinated to this metal. So to remove water, you need a lot of energy. That is also not good scenario. So what we need is easily removable water. So here is one polymer. We got a polymer. This water can be removed even at room temperature just by blowing dry nitrogen or dry air. 50 degrees and easily it will go. Even room temperature it will go. And you can do a number of times this recycling, and it will take again water. And also we can use it as a self-desiccating container. I will show you that. So yeah, so this is the, you can see this is the TGA. This is of monomer, and after polymerization, you can see there is a weight loss. This weight loss is due to removal of water below 50 degrees centigrade in this heating rate. Even at RT, it will go as I said. So about 8.4% is the water that can be tapped by this material. And we have done 30 cycles of hydration, dehydration, and this is the data percentage of, every time it is almost 8% you can get. And next important thing is what relative humidity it will take water. It will take water in Kerala. Kerala is almost 90% relative humidity. Will it take in Gulf countries, for example, Saudi Arabia or other much more drier place? Yes, it will take from 30% onwards, it will take water and relative humidity. So, and this is the isotherm actually. So we can use this material anywhere in the world actually to tap water. Also, we have made a self-desiccating container using this gel. So it's the same gel. Actually, we have made gel and we put in a container actually and polymerized in the container. Now we have placed a bread piece. This is control experiment. This is with polymer and closed and tightly Tefloned it actually, sealed it nicely. And after a few days, you can see there is mildews or a fungal attack in here, but there is no fungal attack because it's desiccating. It's taking water. And to remove water, you don't need very high temperature. Just keeping in drying in air is enough. So this is a self-desiccating container out of which this gelator which we have made. This is the scenario I have told. You can take tap water from this material. Our material, this is an old story. Our material can take double of this, about 18 liters, make 80 liters of water per day per kilogram of this material. So, but that's not the best because this is expensive. This polymeric material which we make is expensive as of now because these are amino acid based material. Nevertheless, we have shown that this kind of chemistry we can use for different applications like soft optics, then oil spill recovery, then also tapping the carbon dioxide and also making also removing metal ions from drinkable water and also making conducting clothes and also for water tapping from atmosphere. These are the guys who have done work. These are the guys already left the group and they are in different parts of the world. Hema is also, she's in Weizmann Institute in Israel now. Rishika and Vignesh is going to US soon. Rishika is searching. She just submit her thesis and Atal will be submitting her thesis soon. And I have some more members currently, but I don't have the pictures here. No, I thank all of them and also DST for this fellowships, the Amanajan Fellowship, Sonayandi Fellowship, and Istrivandam. And thank you all for attending this talk and also the organizers for invitation. Thank you very much.
Thank you, sir. Thank you again for giving me your valuable time and for nice presentation on the development of simple gelators and their potential application by the formation of gel or zero gels. So thanks again, sir. So dear participant, if you have any questions, you can ask directly. Sir, sir, are you getting my voice, sir? Hello.
Hello?
Yeah, are you getting my voice, sir?
No, you were muted some time back. I did not hear you.
Sir, can you show the your sir, second video, sir? Second video.
I have to show it again.
Because
You have,
if possible.
I have to share it again. Yeah. So you have a second video that is with the
Where you have used the powder.
yeah. Right. How do we? Just a second, okay.
Teacher. Okay, sir. Leave it. That's actually, sir. I have one little query, sir. What is the basic principle to design a gelator? What should be the basic principle?
Okay, so that's simple answer actually. So just a minute. So that's what I have told. If it is fully hydrophilic or fully hydrophobic, they will not gelate. So if it is fully hydrophilic, they will be completely soluble in water and completely insoluble in organic solvents. And if it is hydrophobic, completely insoluble in water and highly soluble in organic solvents. So we need amphiphilicity. So we need partially hydrophilic and partially hydrophobic parts. So that's what we have used sugars and amino acids and put some hydrophobic part to make it amphiphilic. So that is one important criteria. And there should be some non-covalent forces like hydrogen bonding, pi stacking, or something which can self-assemble them. That's a criteria.
Okay, sir. Another thing, sir, you have used the mannitol gelators, and then that one used as a powder.
Yeah.
So, how many gram of the your molecule is able to remove the how many ml or of the what is diesel or something you use the crude oil? Is it cost effective
Yeah.
or
So
practically we can use that one?
that is 13% by weight actually. So the sorbent we are finally the best one I'm talking about now. So with the cellulose carrier. So that sorbent, if you have 1 kilogram of that sorbent, it can take 13 kilogram of this one,
Compound.
crude oil, because crude oil is
Okay.
relatively dense, right? So that, so 13.6 times actually.
Okay, sir. That means that powder, whatever you use,
Mm.
that should not be used. I think in large scale. I think.
Yeah, so this one is the powder is very, very little actually. 1% of the total solid material is powder. So I am talking about 13% with respect to the total material, including the cellulose, of which only 1 or 2% is the powder. So it's very, very little, few grams.
Okay. So, dear participants, sir, if you have any questions, you can ask.
Hello, sir. Good morning, sir.
Yeah, good morning.
I have one question, sir. That you have mentioned that the hydrogen bonding is taking place, sir. Right, sir, in the formation of gelatin. So if we in place of you have mentioned about the OH group, right? So in place of OH group, if we have removed that replace oxygen by nitrogen, then the interaction will be same.
Yeah, so that's what we have shown in peptide cases, where we don't have OH. So there we have NHO hydrogen bonding in peptides that also forms gels. So that you cannot say whether it will be same or it will be slightly different, but it can form. So all hydrogen bonding, NHO hydrogen bonding is also strong hydrogen bonding. OHO is also strong hydrogen bonding. So they can form. NH, there should not be an issue.
Okay, sir. Thank you, sir.
Any questions from participant, please? I think, sir, they have no questions. So thank you, sir, for your presentation and your valuable time.
Yeah, I have only prepared for 1 hour. Usually 1 hour, people get bored. People get bored, right? Because
No, sir. It was nice presentation. It was nice.
not because of
Time does not matter, sir.
yeah. Thank you.
I think content should be important.
Yes, I think so.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you very much. I can leave, right? Thank you.
Oh, yes, sir. So, dear participant, we will meet again at 11:45. So, this day 4 session 2. The next our speaker is Professor Aninda Datta from IIT Bombay.